Not too funny. Okay, there we go. Oh, make sure I'm not on mute, actually. That would happen today. No, we're all good. Okay, so just as some quick review, last day we said that the derivative of a function is going to be the slope of the tangent line. Right? And so the derivative of a function is the slope of the tangent line. And then we said the limit definition of a derivative is this. The limit, oh, whoops, I guess I should say what it is. F prime of x, which you're going to read as F prime of x, which really is saying the derivative of f at x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. So that's technically how we would find the derivative, but today we'll look at kind of shortcuts, because functions that behave the same way will always have a similarly behaving derivative. But first, we're going to look at another one of those graphs. So from a graph of f of x, we can sketch a graph of the derivative. Because the derivative is a function as well. So you know what, I'm going to add that, the derivative function, since it's going to have an x in it too. So we did one last day, but here I'll start with a new one. So let's say, as an example, use the graph of y equals f of x to sketch the derivative. Y equals f prime of x. So it's just going to be some random function here. Let's put it like maybe something like that. So our function, right, if we highlight some key features here, right, because to sketch the derivative, and you will have to do this on the second test, right? I'll give you a function like this, and then you're going to have to sketch the derivative. So below it, I'll give you axes like this. And you'll have to use the function up above to sketch the derivative. So first thing we're going to do is we're going to figure out where the slope of this thing is going to be 0. So that's at all these points where we've got either a maximum or a minimum. And that's going to help us out, right? Because here, f prime of x equals 0, right? The slope of the tangent line here at all these points is 0. So that's where we're going to cross the x-axis. So here, here, and here. Make these a little bit bigger. What happens in between doesn't really matter. We just have to get from each of these 3 points. We just increased our numbers by half. Well, Heather's on the line too, so that's 3 people now. I think so. I'm impressed you guys made it. And now there's 2 of you. Yeah. Hey, not bad. 809. So this is where it's going to cross the x-axis. So what happens in between here doesn't really matter as long as we've got our positives and negatives, right? Right, and so here, if we've got a negative slope like we do coming up to the y-axis, right, then our points better be negative down here, right? Because we're reflecting the slope of the curve on this graph, right? So what we want to do is, I'll use a different color here, like green, and say, okay, well, I've got downward slope here, right? So negative slope here, positive slope here between those points, and then I go for all negative down here to the next point, and then it's all positive slopes. So that means that for all the points that have, or for all the sections that have a negative slope, right, I have to be down in the negative. So y is negative. Here, y is positive. And then here, y is negative. And here, y is positive. The y I'm talking about is for the derivative. So maybe what I'll do is I'll say y prime, right? Y prime. Just so it's clear. So that means, okay, I'll use the same color. Down here, we're negative, so it doesn't really matter what it looks like up until this point. And then between these next 2 points, it's all positive, right? But then we know it switches to being negative. And so here, I mean, anything can happen in here, but usually we just draw a little hump. And of course, we could put more effort into it and look at what the exact slopes are. But for us, when we're just sketching the derivative, I don't care too much about that. And then between this point and the next point, it's all negative. So again, we kind of just do a little boop. And then from this point onward, looks like it's positive. So you will have to do one of these on test 2, right, where I give you the curve and I don't give you the function of it because I just want you to look at this and be able to sketch the derivative, right? And so then you're going to identify, okay, where is the slope of the tangent line 0? That's at all those max and mins. And then just look at, okay, is my slope negative or positive? And then reflect that in the graph. down below. Any questions about that one? Okay, cool. No, you said no. Yeah.
Are you going to be using the first definition for words?
Is that the limit definition of the derivative? No. In fact, we're going to start talking about just plain old derivative rules in about 3 pages of notes. So stay tuned. Don't worry. Yeah, we will not be talking or using the limit definition. You will have to find the derivative using the limit definition on test 2 and on the final. But besides that, you can always use those rules to check your work, right? And so, yeah, no, don't worry. I'm just gonna do derivatives later. Yeah. That's good. I know, for some reason, I don't know. Everyone hates limits. I hate limits. Because once you realize that there's a way easier way to do it, it's like, yeah, why would I spend my time doing limits when there's limit laws or differentiation rules? There's limit laws too, but that's not what I meant. One thing that we have to keep in mind is that, good morning, all eyes on you. Slowly but surely, we're filling up. Oh yeah, so the derivative doesn't necessarily exist at every single point, right? And so things that we need to keep an eye out for are essentially places where the slope of the tangent line can't be fixed, right? And so here, so the derivative, derivative may not exist at every point. So what we say that a function is differentiable and I'm not sure I've used differentiable before, but differentiating and taking the derivative bless you, are the same thing. Oops. So that's important, right? If I say differentiate this or take the derivative of this, those are the same thing. So they're interchangeable and I'll use them interchangeably. So a function is differentiable at A if f prime of A exists. That's all fine. It's not very helpful, right? But also, and I'll show you how it wouldn't exist in a second here, but also a function is differentiable. A function is differentiable over the interval AB, open brackets, if f prime of C exists for all C's between A and B. Exists for all A less than C less than B. So that's all fine. I don't really find that very helpful, but those are the facts, right? So if the derivative exists, fine. Sometimes there might be values of x that aren't in the domain of the derivative, right? And so then it wouldn't exist. But let's have a look at what might what might make f of x not differentiable?
I don't know why my phone keeps joining in this game. I don't even have the app on my phone.
Oh. Oh, maybe it's the other Kobe. There's two of you.
It's all the same now.
I don't think he's picked up his test. Yeah, that's a little weird, actually. Yes. K-O-B-Y. Then I don't know. That is really strange. Yeah, that's really weird. And you don't have it on your phone? Weird. I don't know what to say. Yeah, that's really strange. You're a ghost on here. Okay, so what does it look like if f of x is not differentiable at a point? So the first thing is, of course, if just f of a does not exist. So if f of a does not exist, right, meaning that a is not in the domain, and we saw before what it meant for a to not be in the domain, but kind of a common example is if you have a function like this, whee, and then here we are at a, and this is y equals f of x. So then there's a hole here. We can say that the limit exists, right? The limit here would exist, but if we're trying to put a tangent line here at a, then there's kind of this hole here, right? And so if you're trying to put a tangent line, it could go any way or no way, right? Because it's no fixed way. So that's one way that the derivative could just not exist, is if f of a is not in the domain. The second way is if we have a corner or a cusp. Oops. I'd say this is probably the most common way that it doesn't exist. So I'll show you kind of two ways. If you've got something like this at a, again, if you're looking at a and you're trying to put a tangent line here, right, it could go any way. So because there's no fixed way, right, because this tangent line would kind of just hang out on the cusp, I'm going to erase that because it doesn't, if we're looking back, it doesn't really make sense. But the tangent line can go any way. The common function that we know that looks like this would be the absolute value function, right, which has this cusp y equals the absolute value of x. So here at 0, the tangent line coming in from the right, fine, but then we hit this cusp, and then coming in from the left, it's all fine, but then once we get to 0, it's all wonky, right? So it's not able to balance on the cusp is how I kind of think about it. The third option is if you have a vertical tangent line. So a vertical tangent line might look something like, don't know. Whee! So here, let's call this A. Can fit a tangent line, right? But the slope here, rise over run, but the run is nothing, right? So if we're dividing by 0, we can't do that, right? And so here, the tangent slope is undefined. And I'll just clarify, since the slope is rise over run, oops, over none, over run, but the run is 0, right? And so that's why the slope of the tangent line there, if it's a straight vertical tangent, right? So if we're dividing by 0, then it's undefined. So those are the 3 ways that the derivative might not exist, right? It exists everywhere else except at these points A, or presumably it exists everywhere else, but we say that f is differentiable as long as x or f of x is continuous at A, right? So we say that f is differentiable at A or I should say x equals A. At x equals A, sorry, we say if, it's important, if f is differentiable at x equals A, then f is continuous at x equals A. F is continuous at x equals A. I'll underline this if, because I lost it in the beginning. So we say if f is differentiable at x equals A, then f is continuous at x equals A. That's fine, right? Because here, if it had been continuous, right, then it would have been differentiable. Any questions before we talk about higher derivatives? We're so close. Higher derivatives. We can find higher derivatives. So here, what we've been looking at is the first derivative, right? The slope of the tangent line. We can take the derivative of that to find the second derivative, take the derivative of that to find the third derivative, et cetera, and we can go on until our derivative becomes 0. Okay? And so we can find higher derivatives. We can find higher derivatives by taking the derivative of a derivative. By taking the derivative of a derivative. So for example, if we start with f of x and we differentiate, we end up at f prime of x. If we differentiate that, we end up at f double prime of x. This indicates that it's the second derivative. Can do a little example of finding the second derivative. We could keep going and I'll show what it looks like, right? But like I said, we can find the third derivative, fourth derivative, fifth derivative, blah, blah, blah. So if we have f of x is equal to x to the 3 minus x, find and interpret f double prime of x. Okay. So last day we found that the derivative of this thing, and of course we're supposed to do it all on the same day, so then it would make more sense. But last day we found that f prime of x was 3x squared minus 1. So now, if we want to find f double prime of x, that's the same as the derivative of f of x, the derivative of that. Or I guess it's on the f. There. We'll never use that notation. Because the derivative's on the f, not on all of it. So then, using the limit definition, which we're going to shake today, but we've got the limit as h goes to 0 of f of x plus h. Now we're talking about f prime of x plus h minus f prime of x over h. So we've got the limit as h goes to 0, making sure that you keep track of your x plus h's and your x's. And so we get 3 times x plus h squared minus 1 minus 3x squared minus 1 over h. If we expand this, we get the limit as h goes to 0 of 3 times x squared plus 2xh plus h squared minus 1. And then I'll expand that negative in, so then we get minus 3x squared plus 1 over h. Pull that 3 inside, the limit as h goes to 0 of 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1 over h. Just like before, right, we said that everything's going to cancel and that h in the denominator is going to evaporate at some point. And so the 3x squared minus 3x squared goes away, and then minus 1 plus 1 goes away. And now I'm left with terms that only have h's in, or not only, but that have h's in them, which means we'll be able to cancel. So this is the limit as h goes to 0 of, and I'll pull out that common h. Make sure I do it right. 6x plus 3h. Didn't forget a term yet. It'll happen, but not yet. This is going to cancel with this. So now I'm left with the limit as h goes to 0 of 6x plus 3h. If that h goes to 0, I'm left with 6x. I'll keep that color. If we think about y equals 6x, right, then we've just got a straight line with a slope of 6, right, intercept of 0. Maybe I'll change it. So here, to interpret this, this is a maybe I'll say straight line. This is a straight line with a slope of 6 through 0, 0, right? There's no y-intercept, or it's 0, and y is 0 and x is 0, so it goes through 0, 0. So now you've got something that looks kind of like, let's make sure I can draw it nice and steep here. I don't know, something like that. Y equals 6x. Which means the derivative of the derivative, right? So the slope of the tangent line on the derivative function, right, is all negative, or it's all negative leading up to 0, and then it's all positive after 0, after x equals 0. So here, f prime of x is negative. Double prime of x is negative. And here, f double prime of x is positive. We can find even higher derivatives, of course. We can find even higher derivatives. And it's going to look something like this kind of chain. So f of x, if I take the derivative, or if I differentiate, those two are the same thing, right? So f prime of x, if I take the derivative of that, I end up at f double prime of x. Take the derivative of that, I end up at f triple prime of x. Now all these little primes are getting kind of out of hand. And so after the third derivative, what we do is f, and then in brackets of 4 of x. And this is after taking the derivative, of course. Any derivative higher than the third derivative is denoted in brackets. So just as a quick example, if I tell you to find f of 6 of x, I wouldn't, but I could. It'd have to be a huge function to start with. This is the 6th derivative of f of x. You'd probably just use maple for something like that. Right? Derivative, derivative, derivative. So what we're doing here is we're taking the derivative with respect to x, right? And so that's going to come back because it's going to be important that we keep track of which thing we're taking the derivative with respect to. So to, and I'll put it in quotes, differentiate or take the derivative, right? Those two things are the same. To differentiate with respect to x, means to take the derivative treating x as our variable. Treating x as our variable. And that's going to be important to keep in mind for when we actually talk about the differentiation rules, because then we need to keep track of, okay, well, what am I differentiating with respect to, right? So if I'm talking about f prime of x, then I'm differentiating with respect to x. We have to touch on notation, because I do find, even when I took this course, or I shouldn't say even, I don't know, I didn't really pay that much attention, but when I took this course, I found all the notation to be very confusing, because there's so many ways that we can say the exact same thing. And so I just want to list them all here. And then when you see any of them, then you can just say, okay, well, I know all of these are the same thing. So, but first we'll establish the rules. So if we use y equals f of x to indicate that the independent variable is x, this is all blah, 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 because it's what we assume anyways, right? To assume that the x is on the x-axis, fine. To indicate that the independent variable, the independent variable is x, and the dependent variable is y, then some common alternative notations, notations actually, for the derivative are these. We've already talked about f prime of x. We could just as well write y prime, which I think I did at one point. Those two things are the same. We already established that f of x, you could just use y instead if you wanted to, or if you see a y, you can say, oh, well, that's f of x. Then we introduce something like dy dx. How you read this is the dy dx, but differentiate y with respect to x. Right? Or if we want to talk about the function f, so then we can have df dx. Most commonly, we're going to use this little guy, d dx of f of x. So that's saying take the derivative. All these are saying take the derivative with respect to x, right? But of f of x. And so most commonly we use that one. So that's why I highlighted it. But we could also use something like a capital D f of x, or kind of less common, d subscript x, to indicate what we're differentiating with respect to of f of x. Where capital D and d dx are called differential operators. Are called differential. Oops. Stuck on a word here. Differential operators. Put a little box around this just so that we can remember that all of these are the same. So just to show you what things look like, if I have d dx of f of x, that's the same as f prime of x. Or even if I take d dx of f prime of x, that's going to be the second derivative. Or if we do something like d dx of d dx f of x. Okay, I got to scoot this down because I need a little bit more room here. How we would write this is, instead of using the double prime, right, because that's the second derivative, first take the derivative and then take the derivative of that. How we write this is d squared over dx squared f of x, and this is the second derivative. Again, so if we've got d5 dx to the 5 of f of x, that's the fifth derivative. Fifth derivative of f of x. So all of these, and it's kind of the war between Newton and Leibniz. So all these with the differential operators are called Leibniz notation. And so sometimes it'll say, oh, using Leibniz notation. And the reason that we kind of prefer it most of the time is because it hints at units, especially if we're talking about distance and velocity, acceleration. So using differential operators is called Leibniz notation. And it has the benefit of, I call it kind of hinting at the units. So, and it has the benefit of hinting at the units. For example, if I've got my x, which is my position in meters, then if I take the derivative with respect to t over time, right? Usually if we're talking about distance, we're often talking about time as our independent variable. So d dt is saying differentiate with respect to t. WRT is with respect to. So then we end up at dx dt. That's the first derivative, which is going to be the velocity of this thing, which is going to be in meters per second. If we take the derivative with respect to t again, we end up at d squared x over dt squared. This, right, so now things are squared, is our acceleration acceleration, yeah. Which we know is in meters per second squared, right? Notice that the x isn't squared, so the meters just kind of stays meters, and then the time is squared, so then we have seconds squared. We can even find the next derivative. Of course, we could keep going, but it has less and less meaning to us. The third derivative with respect to t is called the jerk, which is in meters per seconds cubed. So we've started our position, and then we take the first derivative to get the velocity of this thing, right? The instantaneous velocity, and then we take the derivative of that to find the acceleration, right? How quickly are we accelerating? And then the jerk is like, right? And so you have to take the third derivative to find the jerks. You guys done with limits or what? The crowd goes wild. So that's the end of chapter 2, and we've kind of covered little things like notation that'll come up and just higher derivatives. We bake those in there too. But like I said, you have to use the limit definition of a derivative on test 2, right, and on the final. But after that, right, we'll just be able to take derivatives using the rules that we're about to establish in chapter 3. Chapter 3 is on differentiation rules. We're going to start small. Derivative of a constant, which if you think about a constant function and you think about what the derivative is, if the derivative is the slope of the tangent line, well, our derivative should be 0, right? And so we'll start there and kind of work our way up. So 3.1 is just derivatives of polynomials. And exponential functions. Like we said, the limit definition of a function of a derivative. The derivative is a function, but I feel like I should be more specific. Man, oh man, f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. So the limit definition of a derivative, this is it. I'm pretty sure one of the questions just says state the limit definition of a derivative. So just be prepared to pull that out. But we've used it so much now that it should be kind of ingrained. So we'll always work to find the derivative. But to simplify things and to avoid having to take the limit all the time, there's established differentiation rules. And so, however, to avoid taking the limit all the time, differentiation rules have been established. Differentiation rules have been established. Through proofs and all that fun stuff. Okay. So we can start by talking about, okay, so if we have a constant function, let f of x equal c, a constant function, well, then the limit as h goes to 0, so here I'm finding f prime of x, of course, the limit as h goes to 0 of f of x plus h minus f of x over h, well, if it's constant, right, it's going to look like this. F of x equals c. The slope of the tangent line, if you're starting here at x and going to x plus h, well, they're just all going to be at c, right? So now we find the limit as h goes to 0 of c minus c over h. Because c minus c is just 0, we're taking the limit as h goes to 0 over h. It's okay that h is approaching 0 because we're not going to be dividing by 0, because 0 over something very, very close to 0 is just going to be 0. And so, just like we thought, the derivative of this thing is just always going to be 0. So the derivative of a constant is 0. So what we say is d dx of c is 0. The derivative of a constant with respect to x, of course, but doesn't matter, is 0. Because there's no x's in there. What if f is a power function? What if f is a power function? So then f of x is x to the power of n, and we're just going to say n is not going to be 0 because otherwise it's not very interesting. We can have a look at, so we can consider x squared, x to the 3, x to the 4th, just to get some idea of how this thing behaves. And so we can find f prime of x is the limit as h goes to 0 of x plus h squared minus f of x, which is just x squared, over h. Here I'll just show that f of x is x squared. The limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared over h. X squared minus x squared, just as we expect, goes to 0. And so now we've got the limit as h goes to 0 of, and I'm just going to cheat and cancel this h right away, of 2x plus h. It's going to be 2x. If we have a look at the next one, f prime of x is the limit as h goes to 0 of x plus h to the power of 3 minus x to the 3 over h. And we're not going to do it, I'm just going to give it to you. But this is if f of x is x to the 3. Then we need the limit as h goes to 0 of, what was it? X to the 3 plus 3x squared h plus 3x h squared plus h to the 3 minus x to the 3 over h. Cancel away here, x to the 3 goes away, and I can cancel an h from each of these. And we end up at 3x squared plus 3xh plus h squared. Oh, I forgot the limit. I'm going to squeeze it on the same page here. As h goes to 0, I'm just left with 3x squared. Do the last one. The limit as h goes to 0 of x plus h to the 4th minus x to the 4th over h, because we don't want to do these limits anymore. This is if f of x is x to the 4th. Clean that up a bit. It's the limit as h goes to 0 of, this thing's huge, x to the 4th plus 4x 3h plus 6x squared h squared plus 4x h to the 3 plus h to the 4 minus x to the 4 over h. Everything is going to cancel more or less. So now we have the limit as h goes to 0 of 4x to the 3 plus 6x squared h plus 4x h squared plus h to the 3. As h goes to 0, the only thing left is 4x to the 3. Whew. If we have a look at the pattern, right, the derivative of x to the 4 is 4x to the 3. The derivative of x to the 3 is 3x squared. The derivative of x squared is 2x, right? And so what we can do is we can summarize this. So we see a pattern emerge. And this pattern extends to any real number n, right? So it doesn't have to be an integer like what we were dealing with. It's just easier to think about. And this pattern extends to any real number n. And it's called the power rule. The power rule says that if you take the derivative with respect to x of x to the power of n, you can rewrite that. So the derivative is n times x to the n minus 1. In business math, we have to sort of touch on derivatives. We only take derivatives of polynomials. And so what happens is you just give it a bump from the right. Power falls down, decreases by 1, then you're done. Why would they need to find the derivative in business math? If you've got a profit function and you want to maximize that profit function, that's at the maximum, right? And the slope of the tangent line is 0. So then you have to take the derivative of the profit function, set it equal to 0 to figure out what x maximizes your profit. That's the only reason they do it. We do it for so much more. As an example, now that we have the power rule, we can find d dx of something simple like x to the 5. That's just going to be 5x to the 4. Right. Bring that power down, decrease it by 1. We're done. We also said it can extend to any value of n. So even if I have something like d dx of root x, well, now I'm taking the derivative essentially of x to the 1/2, right? So the key is going to be to rewrite these things with exponents instead, because now I can bring that exponent down. So 1/2 x to the 1/2 minus 1 puts me at 1/2 x to the negative 1/2, which I can rewrite as 1/2 root x, because x to the negative 1/2 is just 1 over root x. Can even do something like d dx of the 3rd root of x squared. Again, the key is to rewrite this thing with powers instead. So then we're taking d dx of x to the 2/3. Bringing that power down, we get 2/3 times x to the 2/3 minus 1. You can use your calculator or find the common denominator and combine these fractions, but you get 2/3 x to the negative 1/3. So if we rewrite this, that's 2/3 and the 3rd root, oops, 3rd root of x in the denominator. We can use limits to show that if we're multiplying our f of x by a constant, then we can just bring the constant outside the derivative and apply the derivative to the function. We're not going to do that. I'm just going to establish it here. So the constant multiple rule. If c is a constant, and f is a differentiable function, then we can say that if we take the derivative with respect to x of something like c times f of x, we can rewrite that as c times d dx of f of x. So the constant just gets pulled outside. Or if you want to think of it as the derivative attaches to the function, it's fine too. So for example, if we want to find d dx of something like 5x to the 7, that's the same as 5d dx x to the 7. Once I take the derivative, I have 5 times 7x to the 6. So I get 35x to the 6. Even something like d dx of ax, that's a d dx of x. Remember x to the power of 1, essentially, right? Kind of an invisible power of 1. Maybe I'll use a different color here. Because then what happens is we have a times 1 times x to the 1 minus 1. Anything to the power of 0 is 1. So we get a times 1 times 1. It's just a. But from now on, right, if we've just got x, well, the derivative of x is just 1, so you don't have to show it every time. I just wanted to show you where it came from. We can extend this a little bit, right? And if we're adding functions, right, then essentially we've got a series of constants in front. And so the sum slash difference rule, because they behave the same, if we're adding or subtracting, it doesn't matter. We'll establish that if f and g are both differentiable, then the derivative d dx of f of x plus g of x, you know what, since we're doing both here, I'll do plus minus, because it doesn't matter as long as we're consistent, right? If we're adding on the other side too, is going to be the same as d dx of f of x plus minus d dx of g of x. So we can bring that derivative, the differential operator, inside. That's only going to be the case for constants, for adding and subtracting. Right? For multiplying and dividing functions, we have different rules, which we'll talk about next day. But this one is going to be important too. So let's have an example here. If I ask you to find d dx of x to the 8 plus 12x to the 5 minus 4x to the 4 plus 10x to the 3 minus 6x plus 5. Looks nasty, but we've got that the sum and the difference rules. We know we can just bring the differential operator onto the functions of x, right? Bring the constants outside. And so what we get is, I'll write it out, but that's only because we're establishing what's going on here, right? If you just went straight to the derivative from here, that's fine. So d dx of x to the 8 plus 12 d dx x to the 5 minus 4 d dx x to the 4 plus 10 d dx x to the 3 minus 6 d dx of x plus d dx of 5. That 5 we know is going to go away, right? The derivative of a constant is 0. And even the derivative of x with respect to x goes to 1. So we're going to lose a lot of these terms, or at least one. If we take the derivative of each of these individually, right, and kind of string them together, we get 8x to the 7 plus 12 times 5x to the 4 minus 4 times 4x to the 3 plus 10 times 3x squared minus 6 times 1 plus 0. And then if we multiply these coefficients, we get 8x to the 7 plus 60x to the 4 minus 16x to the 3 plus 30x squared minus 6. And then we're done. So here, this is the function, right? So the derivative, remember, is the slope of the tangent line. And so here, this is a function that gives us the slope of the tangent line at any value of x. So this function gives the slope of the tangent line of f of x at any value of x. So let's see here. If I give you a curve and I ask you to find the points where we have a horizontal tangent line, right, what we would do is we would find the derivative of it, set it equal to 0, and solve for those values of x. And so this is the type of problem that you would do in kind of business math, business calculus. And so find the points on the curve y equals x to the 4th minus 6x squared plus 4, where the tangent line is horizontal. What this is actually asking is find where y has max and mins. Right? If we've got a horizontal tangent line, right, that's going to be a maximum or a minimum. We're not really sure. But if we plot this, right, we can use Desmos, but what it's going to look like is something like a W. So, oops. So here, here, and here. So now, if we have, oops, tiny y is x to the 4th minus 6x squared plus 4. We need to find where y prime equals 0. So that means we have to find the derivative of y, which we can also denote dy dx. Right? Take the derivative of y with respect to x, which is going to be d dx of x to the 4th minus 6d dx x squared plus d dx of 4, which I know is just going to go to 0. I get 4x to the 3 minus 6 times 2x plus 0, which puts me at 4x to the 3 minus 12x. Set dy dx equal to 0 to solve for the values of x values of x that make the slope of the tangent line 0, or the values of x that give horizontal tangent lines. So if we have dy dx is 4x cubed, x to the 3 minus 12x, and I'm forcing it to be 0, I have to factor this somehow. I can pull out a common 4x, which is nice. And so what I have is I have 4x times x squared minus 3 equals 0. Therefore, I can say that dy dx equals 0 if x equals 0. And that's from here. Or if x squared minus 3 equals 0, which is from here. If either of those are 0, then I get a 0. So if I have x squared is equal to 3, then x is equal to minus root 3. Both of which are options, right, on our graph, both of which are in the domain. And so we say, so the given curve has horizontal tangents when x equals 0, root 3, and negative root 3. We can plug these into the original equation, right, to find what the values of y are. But so therefore, we have horizontal tangents and I'll just give them to you at 0, 4, right? Plugging 0 into that equation, we end up at 4. Root 3 puts us at negative 5. And negative root 3 also puts us at negative 5. So at 0, it looks like we have a maximum. And at root 3 and negative root 3, we have a minimum. Or minimums. Okay. So we've talked about polynomials. How do we use them? How do we find the derivatives of them? Turns out it's not so bad because we can just put the derivative onto the x. Let's talk about exponential functions. We're going to focus on the natural exponential function, which is e to the power of x. And so the number e is the Euler constant although I'm pretty sure you say Euler. Anyways, can't remember. E is roughly 2.71828818 and can keep going forever. So it's roughly 2.72, right, if we think about it as a number. But you've got an E button on your calculator, so you don't need to do that. But the definition of E is interesting. The definition of the number E is that the limit of, as h approaches 0, of e to the power of h minus 1 over h is just going to be 1. Put a little box around it, although I won't really get you to use that, but it's good to know. So what does this mean? This means that, let's see here. Oh, I did it again. Looks like a C there. This means that out of all the exponential functions, right, b to the power of x, if we have e to the power of x, then the slope of the tangent line, right, because here we know that at h equals 0, right, because e to the x passes through 0, 1, and so now at 0, 1, we've got a slope of 1 for the tangent line. And so we're going to use that. So this means that of all the possible exponential functions, y equals b to the x, the function f of x equals e to the x is the one whose tangent at 0, 1 has a slope f prime of 0 that is exactly 1. Remember that the natural exponential function looks something like this, passing through 0, 1. F of x is e to the x. We know it passes through 0, 1. And this is the natural exponential function. What's neat about the natural exponential function is that the derivative of the exponential function e to the x is just itself. And so here, the derivative of the natural exponential function is d dx of e to the x is just e to the x, which is pretty cool. So no matter how many times you take the derivative of e to the x, you're just going to end up at e to the x. What does that mean in terms of the slope of the tangent line? Well, if the slope of the tangent line is just equal to the value of the function, well, the value of the function is just that y point, right? And so what it means is that the derivative at x equals a is just e to the power of a, right? And which is just the function evaluated at a. So that's kind of cool. So this means this means that the slope of the tangent line to the curve y equals e to the x is equal to the y coordinate of the point. Which is pretty cool. We don't really do examples using what's the derivative of e to the x because it just ends up being itself, so who cares? But we can do an example where we're using the fact that the derivative is just the y coordinate at that point. And so at what point on the curve, y equals e to the x is the tangent line parallel to the line y equals 2x. Right. So we're going to use the fact that the derivative of e to the x is just itself, right? And so we know that the tangent line for e to the x is just e to the x. And so if we need it to be parallel to y equals 2x, well, that means we have to have a slope of 2. And so at some point on e to the x, we're going to get a slope of 2. So we just need to find where that is. And so since y equals e to the x, we also know, because we established that y prime is e to the x. So far, so good. We know at some point we're going to have a slope of 2. It's just going to be a matter of where. So if we denote that point at x equals a, so let x equals a be the point of interest. Right. I'll put in brackets where the slope of the tangent line is 2, right? Because we want it to have the same slope as 2x. So then the slope of the tangent line at x equals a, we can just write is e to the a. But at e to the a, that's where our slope is going to be 2. To be parallel to y equals 2x, we must have a slope of 2. We must have a slope of 2. So we say that e to the a must be 2. And because I want to keep it all on the same page, buy myself another line, 2 lines. So then if I take the log of both sides, I get, a is the log of 2. Therefore, the required point is at a log of, oops, sorry. Skipped a beat here. A e to the a, because that's where we said, okay, well, at a, we're going to have a slope of 2. So, or if we want to talk in numbers, a we decided was the log of 2. E to the log of 2. E to the log of 2 is just 2. So the point that we're interested in is at log 2, 2. Any questions? No. So we're going to do the product rule and the quotient rule next day and start 3.3, which is the derivatives of trig functions, I think. Can't quite remember. But for now, how about we call it a day? No complaints? Thanks for showing up, guys. It wasn't looking good in the beginning. Oh, let's see here. Oh, yeah, cool. All right, bye, guys.